In this question, it is given that 2x is equal to 3 plus 5i and we have to find 2x cubed plus 2x square minus 7x plus 72. So, before we go for the polynomial, let's try to get polynomial from the given data, which is 2x is equal to 3 plus 5i. Actually, to get the polynomial, we have to eliminate the imaginary part, and for that, let's take 3 on the left hand side. So you will get 2x minus 3 is equal to 5i. Now, to eliminate I, let's square both the side. So you will get 2x minus 3 the whole square is equal to 5i the whole square. So on left hand side, we have to use the expansion. So it will be 4x square minus 12x plus 9 is equal to 5i the whole square, or we can say 25i square. But we know that your I square is minus 1, so we will get minus 25. So finally, if you take minus 25 on the left hand side, you will get 4x square minus 12x and 9 plus 25, or we can say 34 is equal to 0. Now let's try to get 2x cubed plus 2x square minus 7x plus 72 in terms of 4x square minus 12x plus 34 by taking long division. Now initially we need 2x cubed. We have to multiply by 1 by 2x. So 1 by 2x into 4x square will become 2x cubed. 1 by 2x into minus 12x will become minus 6x square, and 1 by 2x into 34 will give us plus 17x. Now let's change the sign. So your 2x cube will cancel out. 2x square plus 6x square will become 8x square. Minus 7x minus 17x will become minus 24x, and let's get our remaining 72. Now this time we need 8x square. We have to multiply by 2. So 2 into 4x square will give us 8x square. 2 into minus 12x will give us minus 24x. And 2 into 34 will give us 68. Now let's change the sign. So 8x square and minus 24x will cancel out, and 72 minus 68 will give us 4. So here we can say our function, which is 2x cubed plus 2x square minus 7x plus 72, can be expressed as 4x square minus 12x plus 34 and 1 by 2x plus 2 plus your remaining term, which is 4. But we know that from equation number 1, your 4x square minus 12x plus 34 is 0. So 0 into any polynomial will give us 0. So the only remaining term is 4, which is given in option A. Ta-da! In this question, we have to find the complex number z which satisfied our condition of mod I plus z upon I minus z is equal to 1. So, let's assume our complex number z is nothing but x plus iy. That means we have to find out x and y. So let's substitute in our condition, and for simplification, let's give individual mode. So in numerator, we will get I plus x plus iy, and in denominator, we will get mod of I minus x minus iy is equal to 1. Now, let's simplify our numerator. Collect the real part and imaginary part. Your real term is x, So let's get x over here, and we can take I common from the I and IY. So we will get I into 1 plus y. And if we take denominator on the right side, it will multiply with 1. We will get minus x. From the rest of the terms, take I common. So you will get plus I 1 minus y. So let's try to get the mode. And to avoid the under root, let's square both the sides. On left hand side, we will get square of the real part, which is x, plus square of the imaginary part, which is 1 plus y. Similarly, on right hand side, we will get square of the real part, which is minus x, plus square of the imaginary part, which is 1 minus y. Now here, minus x square is also x square, so x square will cancel out, and let's expand 1 plus y square. So we will get 1 plus 2y plus y square. Similarly, on right hand side, expansion of 1 minus y the whole square will be 1 minus 2y plus y square. Your y square and 1 can be cancelled out, and we can say this minus 2y go on the left hand side, and we will get 4y equal to 0, or we can say your y is equal to 0. That means your complex number z is equal to x plus I0. So your complex number is purely real number which lies on x-axis. Ta-da! In this question, we have to find the maximum value of mod z, where z satisfied the condition of mod z minus 3 by z is equal to 2. Let's call it equation number 1. Here, we are going to use the property of modulus, which is mod of z1 minus z2 is always greater than or equal to mod of modulus of z1 minus modulus of z2. Now here we are considering z1 as a z and z2 as a 3 by z, which should be greater than or equal to mod of modulus of z minus modulus of 3 by z. We assume that mod z is greater than 3 by z. No need to this mode. And if we give individual mode, we will get mod 3 equal to 3, and in denominator we will get modulus of z. Now, from equation number 1, we can say mod z minus 3 by z is equal to 2. So we can replace our left hand side by 2. So we will get 2 will be greater than or equal to mod z minus 3 by z. Now let's take an LCM. Mod z multiplied with 2 will give us 2 mod z greater than or equal to mod z multiplied with mod z will give us mod z square, and your minus 3 will be remain as it is. In further simplification, we can take this 2 mod z on the right hand side. So it will become z square minus 2 mod z minus 3 is less than or equal to 0. Now, if we create the factors, you will get mod z plus 1 and mod z minus 3, which give us two conditions. The first one is mod z plus 1 is less than 0 and mod z minus 3 is greater than or equal to 0. But we know that our modulus cannot be less than 0. So this condition is false. So we have to consider second condition, which suggests that mod z plus 1 is greater than or equal to 0 and mod z minus 3 is less than or equal to 0, which give us mod z greater than or equal to minus 1 and mod z less than or equal to 3. So we can say the maximum value of mod z is plus 3, which is given in option D. Ta-da! In this question, we have to find a complex number a which is equal to under root of 2 into I, which can be separated as under root of 2 and under root of I, or we can say 0 plus I. Now, to get the root of this complex number, we need its real part, which is 0, and imaginary part, which is 1. And we are also going to need modulus of our complex number, which will be under root of real part square plus imaginary part square, or we can say 1. Now, roots of our complex number is plus or minus under root of mod z, or we can say 1, plus your real part, which is 0, by 2. Because your imaginary part is greater than 0, we have to take plus I under root of modulus, which is 1, minus real part, which is 0, by 2. So here we'll get plus or minus 1 by root 2 plus I times 1 by root 2. But we need a, which is actually root 2 into root of our complex number z. And we already find out the root of our complex number, which is plus or minus 1 upon root 2 plus I by root 2. So, if we multiply root 2 with the real part, we will get 1, plus if we multiply root 2 with the imaginary part, we will get I. Finally, your a must be a plus I or minus a minus I. In A option, we have a is equal to 1 plus I, which we consider as a final answer. Ta-da! In this question, we have to find product of all roots of our complex number. Cos pi by 3 plus I sin pi by 3 raised to 3 by 4. Or we can say, according to D Mobius theorem, we can multiply our power with the angles. So we will get cos pi plus I sin pi raised to 1 by 4. Now, to get the fourth root of our complex number, first of all, we have to convert cos pi into cos of 2n pi plus pi, and your sin pi will be converted into sin of 2n pi plus pi whole raised to 1 by 4. Or we can say we will get cos of 2n plus 1, and your pi will be common, plus I times sin 2n plus 1 into pi whole raised to 1 by 4. Now, according to D Mobius theorem, we can multiply the power with the angle, so we will get pi by 4. Similarly, sin pi by 4. Or we can say our z is e raised to I times our angle, which is 2n plus 1 pi by 4, where your n must be 0, 1, 2 and 3. Now let's find out all the roots. For n equal to 0, your first root must be e raised to I times 0 plus 1 into pi by 4, or we can say pi by 4. Then for n equal to 1, your second root will be e raised to I times 2 plus 1 pi by 4, or we can say 3 pi by 4. Then your third term for taking n equal to 2, z3 will be e raised to I times 4 plus 1 pi by 4, or we can say 5 pi by 4. And finally, for the last root, you have to take n is equal to 3. So your last root z4 will be e raised to I times 3 to the 6 plus 1 pi by 4, or we can say 7 pi by 4. But if you remember the question, we have to find product of all the roots. That means we have to find out z1 into z2 into z3 into z4, or we can say we have to find out e raised to I into pi by 4 plus 3 pi by 4 plus 5 pi by 4 plus 7 pi by 4, or we can say we have e raised to I times pi plus 3 pi plus 5 pi plus 7 pi, or we can say 16 pi by 4, which will give us e raised to 4 pi I. Let's expand. You will get cos of 4 pi plus I times sine of 4 pi. Your cos of 4 pi is 1 and sine of 4 pi will be 0. So your final answer is 1, which is given in option B. Ta-da! In this question, your n is a positive integer and we have to find 1 plus I root 3 raised to n plus 1 minus I root 3 raised to n. So let's simplify one by one. Let's consider your first complex number as a z1, 1 plus root 3i. The real part of the z1 is 1 and imaginary part of the z1 is root 3. So we can say mode of z1 will be under root of real part square plus imaginary part square, or we can say 2. Your z1 lies in first quadrant, so we can say your theta 1 must be tan inverse of b by a, or we will get root 3 by 1, which will give us pi by 3. So if we write down our complex number in exponential form, your modulus of the complex number is 2. So let's write down 2 and e raised to I times your modulus, which is pi by 3. But as you know, we have to find out z1 raised to n. So we will get 2 times e raised to I times pi by 3 whole raised to n. So here we'll get 2 raised to n, e raised to n pi by 3, or if we convert into the polar form, we can say cos n pi by 3 plus I times sin n pi by 3. So here we get the simplest form of z1 raised to n. Similarly, we can simplify our second complex number, which is z2. Its real part is 1 and imaginary part is minus root 3. So let's say your a2 is 1 and b2 is minus root 3. So we can get the mode of z1 as under root of real part square plus imaginary part square, which will give us 2. And its argument will be negative tan inverse of mode of b by a, or we can say minus root 3 upon 1, which will give us minus pi by 3. So if we write down our complex number into exponential form, you will get modulus, or we can say 2 into e raised to I times your argument, which is minus pi by 3. But as you know, we need z2 raised to n. So we can say here we'll get 2 into e raised to minus pi by 3i whole raised to n. So we will get 2 raised to n and e raised to minus n pi by 3i. Or if we expand into the polar coordinate, we will get cos n pi by 3 minus I times sin n pi by 3. So we get z2 raised to n, but we need to find out z, which is z1 raised to n plus z2 raised to n. Now from both terms we can take 2 raised to n common, and if we take summation, here I sin n pi by 3 will cancel out and we will get 2 times cos n pi by 3. Or we can say your final answer will be 2 raised to n plus 1 cos n pi by 3, which is given in option A. Ta-da! Here it is given that omega is a imaginary cube root of unity. So we are going to use the property of omega. And we have to find the complex number a plus b minus c into a plus b omega minus c omega square into a plus b omega square minus c omega. Now to simplify this, let's multiply our second and third bracket. So your first term will be as it is. Let's begin from a into a will give us a square. Then a into b omega square will give us ab omega square. And finally a into minus c omega will give us minus ac omega. Now it's time to multiply b omega. B omega into a will give us plus ab omega. Then b omega into b omega square, b square omega cube, and b omega into minus c omega minus bc omega. Now let's multiply minus c omega square. Minus c omega square into a will give us minus ac omega square. Then minus c omega square into b omega square will give us minus bc omega raised to 4. And finally minus c omega square into minus c omega will give us plus c square omega cube. Now let's further simplify. Here we have a plus b minus c. So it will be remain as it is, and let's simplify. Your a square will be as it is. Then we know that omega cube is 1. So b square omega cube will become plus b square. And similarly this c square omega cube will become c square. Now from these two terms we can take ab common. So we will get ab into omega plus omega square. Same way we can take minus ac common. So after taking minus ac common, you will get omega plus omega square. And finally from the rest of the two terms we can take minus bc common. Omega square plus this omega raised to 4 will become omega cube into omega, or we can say omega. Still your a plus b minus c will be remain as it is. To simplify the second bracket, we are going to use the property of omega, which is 1 plus omega square is equal to 0. So we can say omega plus omega square will be minus 1. So your second bracket will be a square plus b square plus c square. This omega plus omega square will become minus 1. So we will get minus ab. Similarly, we also have omega plus omega square over here. So it will be minus 1. So we will get plus AC. And your last term will be plus BC. So here we get a plus b minus c into a square plus b square plus c square minus ab plus ac plus bc, which can be equal to a cube plus b cube minus c cube plus 3abc, which is given in option A. Ta-da! In this question, it is given that omega is equal to minus 1 plus root 3I by 2, which is cube root of unity. Then we have to find 3 plus omega plus 3 omega square whole raised to 4. Now here we can simplify our term by taking 3 common from the first and last term. So we will get 1 plus omega square, and your plus omega will be remain as it is. And we know the property of cube root of unity. 1 plus omega square is equal to 0. So if we take plus omega on the right hand side, then it will become minus omega. So we can say 1 plus omega square is actually minus omega. So let's substitute the value of 1 plus omega. So we will get minus 3 omega plus omega, which will become minus 2 omega raised to 4. Now minus 2 raised to 4 will become 16, and omega raised to 4 can be split into omega cube into omega, and we know that your omega cube is 1. So we will get 16 omega as a final answer, which is given in option C. Ta-da! In this question, you have to find principal amplitude of our complex number sine 40 degree plus I cos 40 degree raised to 5. For applying D Mobius theorem, we need sine within the multiplication of I and cos in a real part. So let's say this sine 40 is actually cos 90 minus 40, or we can say cos 50 degree. Similarly, your cos 40 degree will become sine 50 degree whole raised to 5. So we are ready to apply the D Mobius theorem. According to D Mobius theorem, we can multiply power with the angle. So we will get cos 50 into 5, or we can say 250 degree. Similarly, your second term will be I sine 50 into 5, or we can say 250 degree. Now, to get principal amplitude, let's simplify cos 250 into 360 minus 110. Similarly, we can say sine 25 is also rewritten as sine 360 minus 110. So here our angle is in fourth quadrant. So cos 360 minus 110 will become cos 110, and your sine will be negative. So we will get minus I sine 110. So we can rewrite this polar form into exponential form as e raised to I due to this negative minus 110, which suggests that your principal amplitude of the complex number is minus 110, which is given in option B. Ta-da! Here, your 1 omega and omega square are cube root of unity. Then we have to find 1 minus omega plus omega square, 1 minus omega square plus omega raised to 4 up to 8 terms. So we have to obtain 8 terms. Its first term will always 1. So let's say 1, 1. Your second term having negative sign and its power is increased by 1. So it will be minus omega square, minus omega cube, and so on. And in last term, we have positive sign and its power is increased by 2. So it will be omega square plus omega raised to 4 plus omega raised to 6 plus omega raised to 8 and so on. Now we have to simplify this using higher power of omega. Your first term will be remain as it is. Now in second term, 1 and minus omega square will remain as it is. We can rewrite omega raised to 4 as omega cube into omega. So it will give us omega. So let's write down plus omega. Similarly, in third term, your 1 will be as it is, and we know that your omega cube is equal to 1. So here we'll get minus 1. And omega raised to 6 is nothing but the square of the omega cube. So it will also 1. Now let's move to the fourth term. Your 1 still remain as it is, and we know that omega raised to 4 is nothing but omega. So let's write down minus omega. And your last term, which is omega raised to 8, can be split into omega cube, the whole square, into omega square. This omega cube will be 1, so you'll get omega square. Now, in fourth term, 1 will be as it is, minus omega raised to 5 will become minus omega square. And your omega raised to 10 is plus omega. Your next term will be 1. Your omega raised to 6 is also 1. And omega raised to 12 is also 1. Then in next term, 1 will be as it is. Minus omega raised to 7 will become minus omega, and omega raised to 14 will become plus omega square. And in last term, we will get 1, then minus omega square and plus omega. Here 1 minus omega plus omega square is 1, 2 and 3 times. So we can say we have 1 minus omega plus omega square whole raised to 3. Similarly, 1 minus omega square plus omega is also 3 times. So we will get 1 plus omega and minus omega square raised to 3. And this 1 minus 1 plus 1 will become 1. So we don't have to worry about this one square. We know the property 1 plus omega square is equal to 0. So your 1 and omega square can be rewritten as minus omega. This minus omegas will be remain as it is. And in third term, 1 plus omega will become minus omega square. Your minus omega square will be remain as it is. So here we'll get minus 2 omega whole cube and minus 2 omega square whole raised to 3. Or we can say we have 2 raised to 6 into omega raised to 9, which can be rewritten as omega cube, the whole cube, and we know that omega cube is 1. So finally, your complex number is 2 raised to 6, which is given in option A. Ta-da! In this question, it is given that x plus 1 by x is equal to root 3 To solve this question, we have two tricks. First one is a conventional one, which is related with the quadratic equation. And second one is the shortcut method. I am going to solve using both methods. First of all, let's try to solve using quadratic equation. Initially, we have to obtain quadratic equation, and for that, we have to take LCM. So x multiplied with x will give us x square, then plus 1, and x multiplied with root 3 will give us root 3x. Or we can say our equation is x square minus root 3x plus 1 is equal to 0. Now, to solve this quadratic equation, we need coefficient of x square, which is 1, coefficient of x, which is minus root 3, and constant term, which is 1. So, let's find out discriminant, which is b square minus 4ac. Substitute the values, you will get 3 minus 4 times 1 into 1. Or we can say minus 1. So your root discriminant will be plus or minus I. So we are ready to get the value of x, which is equal to minus b plus or minus your root d upon 2 times a. Just substitute the values. Your b is minus root 3, so here we'll get root 3 plus or minus I upon 2 times 1. Or we can say, if we give individual denominator, we will get root 3 by 2 plus or minus I times 1 by 2. Or if we try to convert into the polar form, we can say your x must be, instead of root 3 by 2, we can say cos pi by 6 plus or minus I times, instead of 1 by 2, we can say it is sin pi by 6. In option D, we have cos pi by 6 plus I sin pi by 6, which we consider as a final answer. Ta-da! So this one is your conventional way. Now, in shortcut method, we have to consider one standard result, in which if your x is cos theta plus I sin theta, then your 1 by x must be 1 by cos theta plus I sin theta, which we know as cos theta minus I sin theta. So we can say x plus 1 by x will be 2 times cos theta. So let's use this case to solve our question. Let's try to compare the given data with our condition. So you will get 2 cos theta is equal to root 3. So you can say your cos theta must be root 3 by 2, which will give us theta is equal to pi by 6. Now, just substitute the value of theta in equation of x, and you will get x is equal to cos pi by 6 plus I times sin pi by 6, which is given in option D. Ta-da! This result is true for cos theta minus I sin theta. Then you will get 1 by x cos theta minus plus I sin theta, and your I sin theta will cancel out, and you will get x plus 1 by x is equal to same result. Use this information to solve this kind of a question. Okay? In this question, your z is r into cos theta plus I sin theta. Or we can say we have the polar form of the complex number. We know that in exponential form, it can be rewrite as r into e raised to I theta. And we have to find z upon z bar plus z bar upon z. We are going to need the conjugate of the complex number. In this case, we will get r into cos theta minus I sin theta. Or we can say in exponential form, we will get r into e raised to minus I theta. Now let's try to get z upon z bar plus z bar upon z. Now let's substitute the value of z, which is r into e raised to I theta, and your z bar is r into e raised to minus I theta. Similarly, in second term, you will get r e raised to minus I theta, and in denominator you will get r into e raised to I theta. Now let's simplify. In first term, your r will cancel out and you will get e raised to 2 theta I, plus in second term, again r will cancel out and we will get e raised to minus 2 theta I. Now if you convert into polar form, you will get cos angle, which is 2 theta, plus I times sine angle, which is 2 theta, plus from second term you will get cos angle, which is minus 2 theta, so cos 2 theta minus I times sine angle, which is again 2 theta. Now here plus I sine 2 theta minus I sine 2 theta will cancel out and you will get 2 times cos 2 theta, which is given in option B. Ta-da! Here it is given that 3 by 2 plus root 3 by 2i whole raised to 50 is equal to 3 raised to 25 into x plus iy, and we have to find x square plus y square. Now here, to get the value of x and y, you can simplify our left hand side using D Mobius theorem, but as you can see, here we need x square plus y square, which can be easily get by taking mod on both sides and apply the property of mod. Now on left hand side, whole raised to 15 will be as it is. Mod of the 3 by 2 plus root 3 by 2 will be under root of real part square, which is 3 by 2, so it will be square, plus your imaginary part, which is root 3 by 2, the whole square. Similarly, on right hand side, 3 raised to 25 will be as it is, under root of real part square, which will be x square, plus imaginary part square, which will be y square. Now on left hand side, this under root can be rewritten as half power, so we will get 3 by 2 the whole square, which will be 9 by 4, plus root 3 by 2 the whole square, which will be 3 by 4 whole raised to 25. Your right hand side will be as it is. Now 9 by 4 plus 3 by 4 will become 3 raised to 25, which can be compared with the right hand side, and 3 raised to 25 will cancel out and you will get 1 is equal to under root of x square plus y square. Or we can say, if we square both the sides, you will get x square plus y square is equal to 1, which is given in option B. Ta-da! In this question, we have to find the real part of 1 minus I raised to minus I. Now, if you observe, we have I within the power. So, to deal with this kind of a term, we have to take log on both sides. So, using the property of log, we can say this power will go within the multiplication of log. To get the log of 1 minus I, we have to convert into the exponential form. So, let's collect the real part, which is 1, and imaginary part, which is minus 1. So, we can say your r, which is modulus of z1, will be under root of a square plus b square, or we can say it will be root 2. Now, here your real part is greater than 0 and imaginary part is less than 0. So your complex number lies in fourth quadrant. So its theta must be minus tan inverse of mod b by, or we can say minus 1 upon 1, which will give us minus pi by 4. So our complex number z1 can be rewrite into exponential form as modulus of complex number, which is root 2, and e raised to I theta, in this case minus pi by 4. So let's substitute the value of z1. Your minus I will be as it is. We will get log of root 2 and e raised to minus pi by 4i. Now, here we have log a into b, which can be separated as log a, which is log root 2, plus log b, which is log e raised to minus pi by 4i. In further simplification, your minus I will be as it is. This log root 2 can be rewrite as log 2 raised to 1 by 2. So, if we apply the property of log, we can say 1 by 2 will go within the multiplication of log. Similarly, your minus pi by 4i will also go within the multiplication of log. So, you will get minus pi by 4i log of e. And we know that log of e is nothing but 1. So we get the simplest form. Now let's multiply I within the bracket. Your I multiply with 1 by 2 log 2 will give us minus 1 by 2 log 2i. And minus I into minus I will become plus I square pi by 4. And we know that your I square is nothing but minus 1. So finally, we will get log z is equal to minus pi by 4. But as you know, we need the real part of the z. So we have to eliminate this log by taking anti-log on both the sides. So we will get e raised to your whole right hand side, which can be simplified as e raised to minus 1 by 2 log 2i into e raised to minus pi by 4. Now, in first term, we have e raised to minus theta I form, which can be converted into polar form as cos angle, which is 1 by 2 log 2, minus I times sine angle, which is 1 by 2 log 2, into e raised to minus pi by 4. Now, if you multiply e raised to minus pi by 4, you will get e raised to minus pi by 4 into cos 1 by 2 log 2 minus I times e raised to minus pi by 4 sine 1 by 2 log 2. So finally, we get our complex number z, and its real part is e raised to minus pi by 4 cos 1 by 2 log 2, which is given in option A. Ta-da! In this question, we have to find a complex number z, which is equal to 4 into cos 75 degree plus I sin 75 degree upon 0.4 cos 30 degree plus I sin 30 degree. Now here 0.4 and 4 can be simplified as 10, and in numerator, if we convert polar form into the exponential form, we will get e raised to I into angle, which is 75 degree, and in denominator, cos 30 plus I sin 30 can be rewrite as e raised to I 30 degree. So your tan will be as it is. We will get e raised to I 75 minus 30 degree, or we can say I into 45 degree. So we can simplify e raised to I 45 degree as cos the angle, which is 45, plus I times sine the angle. Now to get the final answer, just substitute the value of cos 45, which is 1 upon root 2, plus I times sine 45, which is also 1 upon root 2, which can further simplify by taking root 2 common. You will get 1 plus I. So finally, we get our complex number z is equal to 10 by root 2, 1 plus I, which is given in option D. Ta-da! In this question, we have to find minus root 3 plus I raised to 53, where I square is minus 1. Now, let's consider our bracket as a complex number z, which is minus root 3 plus I. So we can say your real part is minus root 3 and imaginary part is 1. So your mode z will be under root of real part square plus imaginary part square, which will give us 2. And your real part is less than 0 and imaginary part is greater than 0. So we can say our complex number lies in second quadrant. So your theta must be pi minus tan inverse of mod b by a. We can say 1 upon minus root 3, which will give us pi minus pi by 6. So your argument of the complex number is pi by 6. So we can rewrite our complex number into the exponential form by modulus, which is 2, into e raised to I times your angle, which is pi by 6. But as we know, we need to find out z raised to 53. So you'll get 2 raised to 53 into 53 multiplied with the power of I, which will give us 2 raised to 53 into e raised to I times 265 pi by 6. So here we'll get 2 raised to 53 and convert into the complex form. You will get cos of your angle, which is 265 pi by 6, or we can say 44 pi plus pi by 6. So let's write down our angle, plus I times your sine angle. So still 2 raised to 53 remain as it is, cos 44 pi, or we can say even pi plus pi by 6 into the first quadrant, where cos and sine both are positive. So we will get cos pi by 6 plus I times sine pi by 6. Or if we substitute the value of cos and sine, you will get root 3 by 2 plus I times 1 by 2. So finally we get z raised to 53, which is 2 raised to 53 into root 3 by 2 plus I times 1 by 2, which is given in option C. Ta-da! In this question, it is given that 1 by x plus x is equal to 2 times cos theta, which suggests that your x must be cos theta plus I sin theta, or we can say into the exponential form it is e raised to I theta, but we need to find out x raised to n plus 1 by x raised to n. So let's get x raised to n, which will be e raised to n theta I. 1 by x raised to n will be e raised to minus n theta I. Now, before we go for the summation, let's simplify into the polar form. This e raised to n theta can be rewritten as cos angle, which is n theta, plus I times sine angle. Similarly, 1 by x raised to n can be rewritten as cos angle, but cos is even function, so it will be plus n theta. Here we'll get minus I sin n theta. Now, if we add equation number 1 and 2, you will get x raised to n plus 1 by x raised to n is equal to cos n theta plus cos n theta will by 2 times cos n theta. And your sin n theta is in plus and minus form, so it will be cancelled out. So tada! We get x raised to n plus 1 by x raised to n is equal to 2 cos n theta, which is given in option A. In this question, we have to find roots of 2 minus 2i raised to 1 by 3. So first of all, let's simplify our inner complex number into the exponential form. So let's collect the real part, which is 2, and imaginary part, which is minus 2. So we can say its modulus will be under root of 2 square plus minus 2 square, or we will get 2 raised to 3 by 2. And real part is positive and imaginary part is negative. So we can say our complex number is lies in fourth quadrant. So its theta must be minus tan inverse of mod b by, or we can say minus 2 by 2, which will give us minus pi by 4. So let's write down our original complex number. 2 minus 2i can be rewritten as 2 raised to 3 by 2 into cos the angle, which is pi by 4, minus I times sin the angle, whole raised to 1 by 3. Now, if we give individual power, 1 by 3 will multiply with 3 by 2 will give us 2 raised to 1 by 2. And to get the cube root of this cos pi by 4 and minus I sin pi by 4, we have to convert angle into 2n pi plus pi by 4. Similarly, sin will also become sin 2n pi plus pi by 4 whole raised to 1 by 3. Or if we simplify the angle, you will get cos of 8n plus 1 pi by 4 minus I times sin the same angle 2n plus 1 pi by 4 raised to 1 by 3. So we are ready to apply D Mobius theorem. We have to multiply power with the angle. So we will get cos 2n plus 1 pi by 4 into 3, or we can say pi by 12. Same thing with the sign, where your n must be 0, 1 and 2. So we are ready to get the roots. Now, first of all, for n equal to 0, your first root will be 2 raised to 1 by 2 cos of 0 plus 1 into pi by 12, or we can say pi by 12 minus I times sin pi by 12 is your first root. Now for n equal to 1, your second root will be 2 raised to 1 by 2 cos of 8 plus 1 pi by 12, or we can say 9 pi by 12, which can be simplified as 3 pi by 4 I times sin 3 pi by 4. For further simplification, if we substitute the value of cos 3 pi by 4, we will get minus 1 by root 2 minus I times 1 by root 2, or we can say minus 1 minus I is your second root. And finally, for the third root, we will take n is equal to 2. So we will get 2 raised to 1 by 2 cos of 16 plus 1 pi by 12, or we can say 17 pi by 12 minus I into sine 17 pi by 12. Now 17 pi by 12 can be rewritten as pi plus 5 pi by 12. That means our angle is in third quadrant, in which sine and cos both are negative. So we will get minus cos 5 pi by 12 and plus I sine 5 pi by 12. So we get all the three roots of our complex number, which does not lie in any option. So your correct answer is option D. Ta-da! In this question, our complex number is 1 plus root 3i raised to 100, and we have to find real part upon imaginary part. Now, for that, we have to convert the inner complex number into the exponential form. So, let's consider inner complex number as z dash, which is 1 plus root 3i, and its real part is 1 and imaginary part is root 3. So we can say its modulus is under root of real part square plus imaginary part square. So it will be 2. Now real as well as imaginary part is positive. So our complex number lies in first quadrant. So we can say theta is simply tan inverse of imaginary part upon real part, which will give us pi by 3. So we can say our complex number z is exponential form of z dash, which is r, or we can say 2, and e raised to I times the angle, which is pi by 3, whole raised to 11. If we give individual power, we will get 2 raised to 100 and e raised to I times 100 pi by 3, or we can say 33 pi plus pi by 3, or we can say odd pi plus pi by 3, which is in third quadrant. So your sine as well as cos will be negative. Now, to get the final answer, let's convert it to the polar form. E raised to I angle can be rewritten as cos of angle, which is 33 pi plus pi by 3 plus I times sine of angle. In further simplification, your 2 raised to 100 will be as it is. Cos 33 pi plus pi by 3 will become minus cos pi by 3. Then minus I times sine pi by 3. If we substitute the values, you will get minus 1 by 2 minus I times root 3 by 2. So here the real part of the z upon imaginary part of the z will be minus 1 by 2 upon minus root 3 by 2, or we can say 1 by root 3 is your final answer, which is given in option C. Ta-da!